Atoms are one of the smallest units of matter in the universe, making up everything from the stars in our galaxy to ants on Earth. Having been so common, you'd think that scientists have measuring these little guys completely figured out. However, that's far from the truth. Their laws are governed by quantum mechanics, a realm of physics comprised of seemingly impossible laws. Regardless, brilliant scientists have worked around this to experiment with atoms in ways we couldn't have imagined. Recently, UBC researchers have revolutionized measurement of the smallest scale, using atoms to measure almost undetectable forces. This study was done by Dr. Kirk Madison, where atoms were used as sensors to indirectly measure small pressures in a vacuum. As discussed in the Modern Science podcast, the background and build-up to this discovery was a long process. Here, we will explain and visualize the actual experiment. Let's begin by taking a look at the apparatus they used. This is called a MAGNETO optical trap. A container containing no atoms sits between 6 cold laser beams that can cool down atoms to 100 microkelvins, which is around 1/millionth of a degree Kelvin. A very dilute gas is added to the container, and the lasers push the atoms towards the center, levitating them and cooling them down. However, since perfect vacuums are hard to establish, particles not trapped by the cold laser trap can knock out the cold atoms from their place in a collision event. The collision cross-sectional size of the two atoms tells us a lot of information about other things going on in the vacuum. Here's why the collision cross-sectional size is important.
Imagine you've got a bunch of billiard balls on a pool table and you're throwing in lots of cue balls. So the billiard balls that were in the center are going to get thrown off the table. And we know that the rate at which you're throwing in the cue balls is going to be the same as the rate of the billiard balls flying out. And we know that the rate is proportional to the number of cue balls coming in, but we don't know the proportionality constant. So we don't know if we always have a one-on-one collision. Sometimes you might throw in a cue ball and it might miss a billiard ball, or you might have 2 cue balls hitting one at once. So to know the rate at which the cue balls are coming in, you need to know the size of the cue ball. And to find the size, we first need to separate the classical collision systems from the quantum collision systems. Let's pretend that these 2 circles represent atoms. For a classical collision to occur, these 2 circles need to touch, so we know that the cross-sectional size is the area of the circle. And for quantum collisions, it gets a little trickier because they don't actually have to touch to collide. So these collisions are very gentle and don't generate much energy. So for the collision cross-sectional area of an atom for a quantum collision is going to be twice as large as that of a classical collision. And to tell which collisions are purely quantum, we need to look at the ones that don't generate enough energy to cause any atoms to escape the trap. Here are some of Dr. Madison's real data. We've got a graph of the loss cross-section versus the trap depth. Trap depth is the minimum energy that a collision needs to generate to result in a loss. So to put it simply, this graph tells us how many collisions generate more energy than the trap depth as the depth is varied. And yeah, this maybe sounds a little confusing, but it's pretty simple. As you raise the minimum energy needed for atoms to escape, you'll get less losses. Let's take a look at this curve. As we move further to the left, you'll see that this curve kind of flattens out, and this tells us that below a depth, or minimum energy, of 100 microkelvin, every single collision generates enough energy to escape the trap. And that's pretty much the maximum number of losses we can get. Now for a trap set up at 30 millikelvin, we'll see that half the collisions generate a loss, and the other half don't. And this midpoint tells us something important. This is where we separate the classical from the quantum. Quantum collisions can generate losses at really shallow depths, but not at deep ones because they don't generate enough energy. And at energies below this point, quantum collisions dominate the system. So from this, Dr. Madison and his team were able to come up with a universal law, a special equation that relates the cross-section to this energy that allows them to calculate the collision cross-section of any atom.
And the shape of this curve here, the shape of that curve, tells you the total cross-section. So that's what this whole paper is about. It's like oh, look at this curve, look how beautiful it is. And then we realize it's not just beautiful, it's telling us something. It's telling us the cross-section.
Then, from there, it's all smooth sailing and simple calculations. Once you have the cross-section, you know the rate. Then you can use the rate to find the density of the gas, and finally use the density to find the pressure.